In this lesson, we're going to look at a different way that you can use the cosine law to solve for missing parts of a specifically non-right angle triangle. Let's begin with a quick review of what we have learned. We've learned that if we have a triangle that's not right angle and we are given an angle with its opposite side pairing and any other piece of information about that triangle, we can solve it. But this condition must be present in order for us to use the sine law. In the last lesson, we learned that if you are given any two sides of a triangle, could be this one and the angle in between them. This is a condition that I like to nickname SAS, or side angle side, and that the triangle can be solved using the cosine law. Now there is one other scenario that we haven't explored yet, and that scenario is as follows. What if we are given only all three sides and no angles? Well, this would be a condition called side, 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 and it also involves using the cosine law, but rearranging the cosine law to solve for an angle rather than a side. Now, I'm not going to take the time to derive the rearrangement of the cosine law as much as I would like to. But instead, what I want you to know is that sine law, cosine law, both versions, their general equations will always be given to you on a summative assessment. And so I'm totally okay if you have these big idea equations from your notes in front of you while you're learning to work with them, because that will mimic what you'd have in a summative assessment too. So going to our last version here of sine, 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 side, 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 sorry, we can solve for either angle A, B, or C to start. And I'm going to choose A just because it comes first in the alphabet. And the way that we can derive the cosine law for the angle A is as follows. We can say cosine A is equal to, and it's going to look a little bit familiar. Remember that opposite sides here are labeled C, A, and B. We're going to take the two sides that are not involved in our focus, which is b squared and c squared. And what we're going to do is we're going to subtract from that a squared. So similar to the first lesson we did, for a given angle and its opposite side, the terms related to those things are on the outside of the equation. And then underneath we have 2bc. So in a similar fashion, we could come up with the cosine law version where we're solving for an angle given three sides for any of the other two remaining angles. We could also do cosine b. We can have minus b squared over here. And then we'll fill in the missing blanks with the remaining two sides. So the remaining two sides would be a and c. It doesn't matter what order you put their squared values in when you're adding them together. I'll put it alphabetically just for fun. And 2ac would go on the bottom here. Similarly, we could do the derivation for finding angle c first if that's where we wanted to start. We'd put cosine c here, we'd put minus c squared over here, and we would use sides a and b to fill in the rest. A squared plus b squared, and 2ab on the bottom. So you don't need to have all three versions of the cosine law present to solve a triangle. You can see that because of patterns, you can easily derive them. So let's go to an example of how we can use cosine law when all three sides are given. And again, remember, this is not a right angle triangle. It can be, but we don't need to use the cosine law for right angle triangles because we have SOHCAHTOA instead, and it's so much faster.